One of our co-hosts for this Congress is the Institute for Law and Systems Research at the University of San Diego Law Faculty, and lawyer and professor Paul C. Walmuth is the director, and he was going to come and address the conference as well as showing segments of this tape. He had some serious family problems, and so a few weeks back we rearranged things, and we are now instead going to show the full tape. But as he said, since he wrote the narrative for the tape and he narrates it, you will have his voice at least present as we show this film, which takes the full film about 28 minutes, and then we will break for lunch. The film relates to a very exciting pilot project which is being pioneered both by the Institute for Law and Systems Research and the state of California. And also, I believe there's also a third party at the University of Nevada. And what they are doing is using systems principles to try to understand better the dynamics of processes that come under various kinds of regulatory regimes, looking at the real world and then trying to move back to understand the underlying principles in terms of our understanding of systems dynamics. So, as he puts it in his introductory blurb here, the film is called Infrastructure, and it's a pilot project in a planned series of experimental multimedia compositions to penetrate the structure and dynamics of complex regulatory systems. And the first pilot here uses the transparency, as he puts it, of vehicular and pedestrian traffic patterns, which can be observed and photographed and filmed, to illustrate the dynamics of these regulatory patterns. So it's in effect an example for how the series will ultimately probe more deeply into more complex and less visible forms of social regulation. So with that, if we're ready to go, we'll roll the film. We'll have to turn the lights off. Yep. Okay.
The production of this film is an experiment in accessing the dynamic infrastructure of regulatory systems. It constitutes a novel scholarly composition using state-of-the-art digital editing technology to integrate visual, sound, and narrative components. The project exploits the unique transparency of contemporary traffic regulation to build a prototype for the analysis of a variety of regulatory systems, most of which bear little surface resemblance to traffic. The claims made here are offered as hypotheses receiving provisional empirical support from the materials presented, but requiring considerably greater investment in research for either confirmation or refutation. The primary objective of the film is to serve as a brief for funding and other support for the more extensive research required. At a later stage, we seek to integrate the film itself into the very dynamic infrastructures that it has been produced to illuminate. Its integrated potential relies upon its impact on the viewer, an impact which trades simultaneously on recognition of the phenomena presented and receptivity to the insight evoked. A train station is a good place to observe and document a wide range of human activity and behavior. Well-placed cameras catch human beings in transit, absorbed in their journey as they interact with the design, facilities, and structure of the station and with each other. With the help of tools for empirical analysis, patterns of action and response previously obscured can be brought into focus. Movements commonly undertaken but hard to grasp can be highlighted and further illuminated by processes of isolation, comparison, and integration. The stream of passengers in a train station lobby, in contrast to persons differently occupied, has a distinctive organization. Cramped congregations placing bets at a racetrack, for example, are caught by a camera passing through tightly packed lines in punctuated fashion. Passage through the train station lobby, on the other hand, is both more freely flowing and more random in organization, as persons pass one another at more or less comfortable distance. Another mode of passage is portrayed in the channeling of passengers, sometimes in close proximity to one another, through doorways and corridors of the same station. Here the flow is markedly both smoother than at the racetrack and less random than in the station lobby. The flow up the more confined channels of escalators is still more organized, though punctuated patterns periodically appear on close observation of denser clusters of travelers. A similar pattern is visible in movement through turnstiles and ticket checkpoints. As the camera shifts to the train platform, a robust rhythm of filling and emptying can be observed, with the platform and the train serving as filling chambers out of which passengers, cheek by jowl, are spilled off one and onto the other. Outside of the station, the modes of human transport just observed are reorganized in new combinations with both similar and some different results. Shots isolating individual and small groups of pedestrians reveal organization at smaller social scales. As the camera pans back into the crowd, larger ensembles of pedestrians on the move regain the foreground. The crowd can move en masse with surprising grace, despite the proximity of individuals to one another. The undulating melee of the crowd, leaving and entering the train at the platform, now stands out in sharp contrast. Blood flowing through a human cardiovascular system seems to reflect and perhaps help us to recognize these contrasting modes of transport. Recurrent pumping action is comparable to the rhythm of racetrack betting. The streams of blood flowing outward and back to the heart, some more punctuated, some smoother, resemble movement in the channels leading into and out of the train station lobby and to and from the platform in trains. Loose aggregations of pedestrians on the street a few blocks from the station experience the time and distance compatible with a chat. In rush hour, similar individuals, more tightly clustered, can be observed in more rapid, determined, and serious movement towards the office, the station, or other compelling objective. The pull of these various destinations, external to the demands of regulating transport, help shape the tempos and rhythms observed. Entry Entry into and passage through the station lobby can now be integrated with these other stages of the extended journey. The mode of carriage shifts with the channeling of the ensemble through the doorways, corridors, and conveyances in the station. This now recognizable but variable chain of transport, channeling and randomness, pulsation and smoothness are knit together into a composite and elongated organization of stages and sequences, in the aggregate resembling a pump, remindful again of the cardiovascular system. The human heart dominates the pacing of the cardiovascular pump, responsible for keeping us alive and adaptable to the demands of daily activity. The chambers of the heart collect blood for dispersal around the body, a dispersal that, in general, is punctuated upstream but smoother downstream. The relative smoothness downstream partially but incompletely masks the pumping action upstream, thus creating the appearance of more smoothness overall than on more careful observation turns out to be the case. Mediating and sustaining the balance between the explosive contractions of the heart muscle and the relative smoothness of the flow outward are electrical impulses provided by coordination of the central and peripheral nervous systems. The pumping action is reintroduced by strategically placed valves downstream. A heart inadequately supported by this built-in signaling system can receive reinforcement by implantation of an artificial signaling device producing periodic shocks, revealingly designated a pacemaker. Outside the train station, the pulsations of pedestrian traffic interact with the thrust of another kind of traffic harnessed for propulsion through the city. Unlike travelers on foot, horse-drawn vehicles, and bicycles, all of which are propelled by flesh and blood energized by metabolism, automobiles are equipped with fuel processing internal combustion engines capable of exponential amplification of the action of a single foot. The scene for channeling this kind of human traffic shifts from the structures and facilities inside the station to structures outside suitable for regulating the powerful, traveler-operated steel containers that have come to dominate surface transportation in the 20th century. The melee that was transport on streets in New York and other big cities early in the century has given way to a distinctive organization of urban traffic movement, now taken for granted. A rapidly played report of the camera panning up Park Avenue reveals a traffic pulse as the flow of crossing traffic periodically alternates with the more dominant flow along the avenue. Adequately coordinating these dense crossing flows presents a regulatory problem comparable to that of cardiovascular flow, and the visible pulsation of the traffic suggests a comparable solution. Inside their cars, drivers and passengers have always experienced this pulse as a rhythm of stop and go, brake to accelerator to brake. Always, that is, except for the open road and, since mid-century, the superhighway. While stop and go is still palpable in the procession of cars along Park Avenue, some of the annoying irregularities in the older version of stop and go have been smoothed out. The more modest shocking of motorists into coordination by the traffic officer, the stop sign, and the periodic traffic light has been replaced by domination along major thoroughfares like Park Avenue of coordinated traffic lights capable of semi-automatic adjustment to suit different densities of traffic at different times of day and night. This technological achievement has been supplemented in recent decades by automated green, yellow, and red arrows and allowable turns on red. The result has been to superimpose faster and smoother flow, especially on the major streets, over the still visible stop-and-go pulse. Thus has city traffic, at least under favorable conditions, been harnessed into the faster and smoother flow that is captured by the camera as it pans outward towards the major roads and superhighways, whose engineering has come to dominate the pacing of traffic flow not only between cities, but within them. Highways, even those retaining some of the old pacemaking ingredients, traffic lights and stop signs, allow quicker and smoother traffic flow by lessening the intrusion of intersectional traffic. The engineering of superhighways consummates the logic of this design feature by wholly substituting entrance, merging, and exit paths for intersections. Where highway traffic is uncongested, it is not until these more facilitated pathways lead back to more conventionally paced traffic that drivers are reminded of the stop-and-go undercurrent of the superhighway. An undercurrent, as we shall see, that can become visible under less favorable conditions, even on the faster roads. The regulation of driving under both stop-and-go and primarily go conditions have in common the maintenance and stabilization of an ephemeral driver resource known as headway, the distance between one's own car and the car immediately ahead. Where stop-and-go prevails, this resource can only be distributed in accordion-like fashion. The control and other devices that constitute the urban and suburban traffic pacemaker, including early and continuing driver training, enable enough predictability in driver behavior to keep cars moving without collision despite the volatility in the headway resource. Accidents result when headway and its stability is overestimated, a consequence of the breakdown of drivers' calculations as they interact with pacemaking devices and each other. Contributing to driver miscalculation is the susceptibility of headway, like other resources, to appropriation. Well-engineered pacemaking can reduce the likelihood of headway overestimation. But the ongoing calculus at any moment can be disrupted by the behavior of individual drivers. As we approach the entrance to the superhighway, a ramp meter, a variant on the traffic light, helps to integrate the stop and go of slower traffic with the rapid flow ahead. A succession of merging maneuvers with other drivers shows how well prepared all drivers must be to engage in headway management on the fly, especially at superhighway entrances and exits. Aerial footage of Los Angeles freeways portrays the choreography of high-speed headway management facilitated by contemporary civil engineering as it conscripts average driving skill. Losing sight of the off-road antecedents of this impressive procession of driver ensembles creates the illusion that anything resembling a pacemaker has disappeared. It is as though highway engineering, like other contemporary human interventions, has reached a landmark in the pacing of human activity. But as congestion mounts either overall or at rush hour, reminders of an underlying pacemaker begin to appear, reminiscent of the demands of headway management under more urban stop-and-go conditions. This occurs not only near entrances and exits, where stop-and-go has always been more evident, but all along the road. The tendency of more aggressive drivers to appropriate the headway of others is now shared by less aggressive drivers. The gains brought by half a century of highway engineering are jeopardized as the social calculus of headway management is undermined at speeds making the calculus significantly more difficult. Highway engineers have reacted by efforts to refacilitate disrupted superhighway flows. Using increasingly sophisticated computer simulation strategies, they have isolated the phenomenon of traffic shock waves as responsible for breakdowns in the calculus of headway management. But shock waves, tightly packed but temporary queues of drivers propagating backwards in lanes of traffic, signal the revitalization of the old pacemaker, but harder to recognize outside of its native urban stop-and-go setting. Shock waves, the troublesome headway accordions of the superhighway, constitute a regressive but nonetheless robust means, at least for now, to keep traffic moving where no conventional or other signals are available to smooth the flow. Unavailable because of the very removal of intersections central to the innovation of superhighways in the first place. Traffic engineers in Europe, choosing like the rest of us to treat the shock wave as a disease rather than default remedy, have rallied around a proactive solution suggested by their congestion simulations. They have identified a relationship between traffic density and driving speed, which left to itself leads to the shock waves pictured here. Systematic experiments over the last 10 years on highway segments previously subject to snarls in Germany, Holland, and the United Kingdom have demonstrated the ability to get drivers to reduce speed to levels matched to particular traffic densities, bringing about a smoother, less stressful, and sometimes faster journey. The means for accomplishing this are depicted in the following video, now utilized in the training of officials responsible for implementing the new strategy in the United Kingdom.
The M25 Controlled Motorway Pilot Scheme uses a new generation of motorway signals known as Controlled Motorway Indicators, or CMIs. These are linked to speed measuring and recording equipment, consisting of a GATSO speed radar, 35mm camera and flash, to provide a highly reliable and robust evidence-gathering system. The combined CMI and speed equipment system is fully approved for use on British motorways by the Home Office. As a driver approaches, he will clearly see signs at all entries informing him he is entering the controlled motorway area. Besides gantry signals on the main carriageway, all entry slip roads onto this section of the motorway are equipped with post-mounted signals displaying the current speed limits in force. The CMIs have been specifically designed for high visibility. In fact, with a clear line of sight, each signal can be seen from a distance of 500 meters, about the length of 5 football fields, and is legible from around 300 meters. The red ring around each speed limit, indicating it is a mandatory restriction, has been developed using colors which enable even those with color sight deficiencies to see it clearly. All the signals can be set either automatically or by police operators and are able to display a range of speed limits from 20 miles an hour to 60 miles an hour, as well as other symbols such as the red X indicating a lane closure, divert and leave motorway arrows, fog, and the end of restriction roundel. Mounted behind the signal at the back of the gantry is the speed measuring and recording equipment. Although facilities will be provided over each lane, initially only one will actually have the speed measuring and recording equipment in place. This equipment, however, can be moved from lane to lane. A number of gantries have been fitted with the equipment within the scheme. The speed measuring and recording equipment consists of a GATSO speed radar, 35mm camera, flash, and CMI interface. It possesses numerous fail-safe mechanisms to guarantee its correct operation. For automatic enforcement of mandatory speed limits to occur, however, a number of criteria must be met. All signals on a gantry must display the same speed limit. The enforcement unit must also undergo and pass numerous built-in integrity checks. Following the change in speed limit, a suitable delay must first have elapsed to enable oncoming drivers time to react. When and only when these and other stringent criteria are met will the system begin to enforce. A motorist exceeding the set limit passes beneath the gantry. The enforcement system is triggered and takes 2 independent speed measurements in line with Home Office requirements for an automatic enforcement system. The radar measures and registers the car's speed, and the GATSO camera takes 2 photographs from which the secondary speed measurement is obtained. All the evidence, including the speed measured by the radar, is automatically recorded onto the film medium. The film is removed from the camera and taken away for analysis. After processing and printing, the 2 photographs are then examined. Photograph A shows the offending vehicle and its registration number, along with the film number, offence number, gantry address, A or B carriageway, lane number, date, and time of violation, speed of the vehicle as measured by the radar, speed limit set at the time of the offence, direction of travel, and time since speed limit was set. The second photograph, photograph B, shows the offending vehicle half a second later. By comparing A with B and using the special grid markings on the road surface, it is possible to accurately work out the car's speed, thereby providing the secondary method of measurement and corroborating the evidence of the GATSO speed radar. The 2 photographs can then be used as evidence by the police for the purpose of issuing a warning letter, or, if deemed more appropriate, a notice of intended prosecution. Every aspect of both the CMI and the speed measuring and recording equipment has been carefully designed and rigorously tested to meet Home Office requirements. The evidence produced has been carefully prepared and checked to ensure it is of the same level of integrity as has been built into the system.
Why traffic engineers and law enforcement have succeeded in bringing the results of computer simulations to fruition on the highway is not entirely clear. We advance the hypothesis, requiring testing in future research, that the means of law enforcement just described subtly intermingle with reduced costs of headway management, subjectively registered by drivers as reduced stress, as speed reductions are automatically matched to increases in traffic density. The result is more following behavior and less lane changing. That is, a relinquishment of headway appropriation, at least by the bulk of average drivers. Manipulation of the camera equipment at the experimental site has shown that camera flashes, even from unloaded cameras, are crucial to conscripting drivers' cooperation, perhaps becoming the heart of a revitalized pacemaking system without being specifically designed to serve this function. The regulatory effect has held constant during extended periods when no film of violations has been processed, so long as flashing continues as usual, despite an estimated 5% relationship of prosecutions and convictions to violations committed. Speeding and headway appropriation significantly increase when flashing ceases, whether or not film is being developed. We want to suggest that the success in using technology in education to re-regulate the utilization and appropriation of headway as a vital resource in Europe should be considered in efforts to re-regulate other systems, even those like commercial markets which bear little superficial resemblance to automobile traffic. For example, how the recent injection of new technology into the traditional operation of the Chicago Board of Trade has facilitated the trading of commodity and mercantile futures may best be understood in this light. A key to addressing the tragedy of the commons may be the ultimate stake in future research of this nature, given adequate funding and support.
I think this video, which is being used as a fundraising tool, among other things, classifies as an example of that old vaudeville saying, "No applause, please, just throw money." We can break for lunch, but